The large-scale adoption and deployment of IoT infrastructure and services in the various sectors of the economy will significantly increase the energy demand from the IoT cyber-physical infrastructure, like sensors and actuator devices, through the transport network infrastructure and the cloud computing infrastructure. It affects most layers of the reference IoT architecture. Therefore, one of the design goals of Green IoT is to develop effective strategies to reduce energy consumption. These strategies should be deployed across the IoT architecture stacks. That is, energy-saving strategy should be implemented across all the IoT layers, including perception layer, transportation layer, application layer, energy and sustainability management layer. That is a new, abstract concept that spans across the perception, transportation, and application layers. At each layer, various energy-efficient strategies are implemented to reduce energy consumption. Much energy is used to perform computation and communicate at the multiple layers. A significant amount of energy is saved by deploying energy-efficient computing mechanisms like hardware and software, low-power communication and networking protocols, and energy-efficient architectures. Energy efficiency should be one of the main goals of Green IoT systems: design, manufacturing, development, and standardization. The energy-saving mechanisms may vary from one layer to another, but they can be classified into the following categories: green hardware, green communication and networking, green architectures, green software, green security, and green policies. A realistic approach to significantly reduce the energy consumption in IoT systems or infrastructures is to dramatically improve the energy efficiency of hardware systems, because a large proportion of energy is used to power the electrical and electronic hardware, such as computing nodes, networking nodes, cooling and air conditioning, power electronic systems, security, and lighting systems. Recently, much attention has been paid to improving the energy efficiency of hardware systems in ICT infrastructures, especially in the IoT industry. The energy-saving mechanisms in IoT infrastructures include reducing the size of the hardware device, using energy-efficient materials, energy-efficient hardware design, turning off idle devices, and energy-efficient manufacturing. To achieve the Green IoT vision, deploying energy-efficient hardware in all layers of the IoT reference infrastructure is essential. Green IoT hardware is not limited to energy-efficient hardware design and hardware-based energy-saving mechanisms in the IoT infrastructure, but also includes sustainable hardware approaches, such as using disposal and recyclable materials to manufacture IoT hardware, incorporating energy harvesting systems into IoT systems or infrastructure. Green or sustainable computing is developing strategies to maximize energy efficiency and minimize the environmental impact from the design and use of computer chips, systems, and software, spanning across the supply chain from the extraction of raw materials needed to make computers to how systems are recycled. Green computing strategies can be implemented in software or hardware. Hardware accelerators, such as GPUs and data processing units, are major green computing drivers because they provide high performance and energy-efficient computing for artificial intelligence, networking, cybersecurity, gaming, and high-performance computing services or tasks. Green software goes back to the beginning of the computer era in terms of code efficiency and compactness. For example, it uses assembler and C or C++ code that is far more efficient in terms of performance and memory than modern high-level programming languages such as Python or Java. It also emphasizes the importance of proper software-based energy management, such as asynchronous routines, use of interrupts, and sleep modes. Interestingly, about 19 terawatt-hours of electricity per year could be saved in all artificial intelligence, HPC, and networking computing tasks could be offloaded to GPU and DPU accelerators. Communication infrastructure is a significant energy consumer in IoT systems as device-generated data increases exponentially. Strategies to enhance energy efficiency include low-power networking and communication technologies such as use of LoRa and LoRaWAN, energy-efficient data transmission in terms of data aggregation, like transmission scheduling concerning the green energy availability and network load to avoid surges. Network level offloading of computation using edge and fog computing to minimize transfers. Energy-efficient communication techniques such as transmission power control and sleep cycles. Energy-efficient IoT systems are built around architectural frameworks that integrate energy optimization across all layers of the IoT ecosystem, including device, network, and application levels. Key strategies include hierarchical architectures. Layering devices into hierarchical systems allows for task and resource distribution, improving energy efficiency. Decentralized processing. Leveraging edge and fog computing reduces dependency on energy-intensive cloud operations, curbing overall system power consumption. Optimized software plays a critical role in reducing the energy footprint of IoT systems. Besides computing considerations presented in the chapter above, the following approaches are efficient. Energy-aware algorithms. Algorithms that minimize computational complexity, reduce CPU cycles, and energy usage. Dynamic software updates. Incremental updates allow IoT devices to maintain optimal functionality without requiring frequent firmware changes, thus saving energy over time. AI-based optimization. Machine learning algorithms predict and adapt energy consumption patterns based on usage, ensuring operational efficiency. Developing advanced design and manufacturing processes to produce energy-efficient chips is one of the strategies currently being used to reduce energy consumption to achieve the green computing and communication goals. An example of how advanced manufacturing may significantly reduce energy consumption in computing and communication devices is the A-series chips used in Apple's iPhones. The power consumption of the 7nm A12 chip is 50% less than its 10nm A11 predecessor. A common technique is manufacturing specialized chips for signal processing, like in 5G and approaching 6G mobile network devices. Power-saving techniques like dynamic voltage and frequency scaling are also implemented to adapt energy usage based on real-time load. Regulatory frameworks and corporate policies play a foundational role in driving energy-efficient IoT adoption. Global standards. Policies encouraging compliance with energy-efficient standards like Energy Star, IEEE standards for energy-efficient networking foster widespread adoption of sustainable practices. Incentives for energy-efficient designs. Governments and industry bodies can offer subsidies, tax benefits, and grants to encourage the development of energy-efficient IoT systems. E-waste management regulations. Effective recycling and disposal policies ensure that IoT components are responsibly managed, reducing their environmental impact.